Okay, we are going to learn the extended Euclidean algorithm, which is essentially doing the Euclidean algorithm backwards. So we're going to have to start by doing the Euclidean algorithm and then we'll go backwards. And before we do that, let's practice the Euclidean algorithm. So we'll do one example that's pure practice and then another example where we practice and then go backwards. Sorry with the split screen here. I'm going to try and remind you how to do this on the calculator. So the left-hand side looks a little small, make it bigger after we use the calculator. So the first question, if you can't read what those numbers say, we're trying to find the GCD of 125 and 86. So we know that we need to start out by writing 125 is 86 times something plus something. And we remember the way that we do that is we do 125 um, divided by 86. Okay, that gives me 1.45 something. So the whole number there is 1. So the 1 goes next to the 86. And now I have to figure out what the remainder is. So I essentially solve this equation for the remainder. I subtract the 86 times 1 over. So I do 125 minus 86 times 1, which is just 86, and that gives me 39. So my remainder here is 39. Remember the two numbers next to that I carry down are the 86 and the 39. So I have 86 is 39 times something plus something. So now I'm going to do 86 divided by 39. The whole number there is the 2. So I'm going to keep the 2 for the next to the 39. And then I will do 86 minus 39 times 2. What I'm doing here is I'm solving for the remainder in that equation. That gives me 8. Again, I'm going to carry down the 39 and the 8. So I have 39 is 8 times something plus something. These, at this stage, you could probably do this in your head, but I'll keep showing you how to do it on the calculator just in case you were confused. So if I do 39 divided by 8, the whole part there is 4. I do 39 minus 8 times 4, and I get a remainder of 7. Now I have 8 is 7 times something plus something. Okay, I'm not using the calculator anymore. This should be 7 times 1 plus 1. And then the last step, which I sadly don't have room to write under here, is going to be 7 is 1 times something. So remember, this is the 7 and the 1 that I'm carrying down now. So 7 is 1 times 7 plus 0. We've gotten down to a remainder of 0, which means that the previous remainder is my GCD, which is the 1 here. So the GCD here of 125 and 86 is 1. So those two numbers have nothing in common. So that is what we've got there. Now we're going to switch over to full screen so we can see all of this nicely. Okay, so that's the GCD of those two numbers. Okay, that's all we're going to do with that practice problem. So for the next one, we want to show that one's the greatest common divisor of 83 and 25. So again, we're trying to show that one's the GCD of those two numbers. We're going to do the Euclidean algorithm here. I know that we could do this just by factoring, but we'll do the Euclidean algorithm so that we can do some more with this answer as well. So I'm going to write 83 is 25 times something plus something. You should try this on your own. Don't watch me do it. So it turns out to be 3 and 8. And then I'm going to write 25 is 8 times something plus something. So it's going to be 8 times 3 plus 1. And then I'm going to say 8 is 1 times something plus something. So this is 1 times 8 plus 0. This tells me that my GCD is indeed 1, so that's the biggest number that divides both 83 and 25. Perfect. Okay, what we're going to do at this step is we're going to use the Euclidean algorithm. And what we're going to do is we're going to use the Euclidean algorithm to write 1 as 83 times some number plus 25 times some other number. We're going to look for integers x and y so that this statement is true. Okay? You might be able to like guess and check what numbers would work here, but I don't know that it's going to be so easy to do that. So what we're going to do, this is going to be the backwards Euclidean algorithm, and this will work in general. And in class, we'll learn an easier way of doing this. But how the backwards Euclidean algorithm works is it says, forget about this last equation, the one that has a 0 in it, we're going to get rid of that one. So I'm just going to erase that one. Okay. Um, We're going to take the other equations that we have and we're going to solve them for the remainders. So we're going to solve each of these for their remainders, which means I'm going to solve for the 8 and for the 1. So when I solve for 8, I do 8 is 83 minus 25 times 3. So I literally just moved subtract to the 25 times 3 over to the other side of the equation. Okay, I'm not going to simplify this at all. I'm going to leave it like this. And then when I do that with the other equation for the 1, I'm going to solve for 1. Which means I'll subtract the 8 times 3 over. So this is 25 minus 8 times 3. Okay. So what am I going to do now? So this last equation is kind of in the form I want. I want 1 is equal to something. Okay. And I want it to be equal to something that has a 25 in it, but then I also want it to be equal to something that has an 83 in it. Right now, this piece doesn't have any 83s in it. So what I'm going to do is I'm going to take the previous remainder. We figured out what 8 was equal to in terms of 25 and 83. So I'm going to replace the 8 in here with this expression because 8 is equal to that whole expression. Okay, so this is kind of weird, but kind of bear with me. We'll do 2 examples of this and we'll do another example in class and then we'll learn an easier process. But it's instructive to see how this works. And you can kind of see that we're doing the Euclidean algorithm backwards in some sense here, using the remainders. So let's see, how is this going to work? So I'm going to have 1 is 25 minus, now this is where I'm going to replace the 8 with this expression. So 83 minus 25 times 3, all of that times 3. Okay. What I notice now is at this stage, I have a 25, I have an 83, I have a 25. This looks pretty good. I need to rewrite this just a little bit. So let's do that. So what am I going to do here? I'm going to multiply the 3 through. And I'm going to be very careful not to simplify too many things. I want to keep the 83 and the 25. I don't want to simplify those at all. So I'm going to have 1 is equal to 25 from this 25. When I distribute the 3 to the 83, that's going to be minus 83 times 3. I'm not going to try and simplify that at all. Okay. And then here, I'm going to have a minus and a minus. So I'm going to get a plus 25 times 9. And that's because I multiplied the 3 and the 3 together to get the 9. So that's, I'm keeping the 25. I'm not changing the 25s or the 83s because I want those in my final answer. Okay. So now I'm going to simplify things just a little bit. So I have 25 plus 25 times 9. So we could think of this as a 25 times 1. So I have 125 plus 9 25s. That's going to give me 25 times 10 total. So this is going to give me 25 times 10 minus 83 times 3. Okay, so we finally got this in the format that we wanted. Essentially, the 25 and the 83 are in the opposite order, but that's okay. So we have been able to write 1 as a combination of 25 times some integer plus or minus 83 times some integer. Okay. You can double check your work, like type this equation into your calculator and make sure it's indeed equal to 1. Okay, it should be. So this equation on its own might not seem super useful, but if you think about what we did at the beginning of class this week, we had several times where we said getting an equation of this form will be useful for multiple reasons, for things like finding inverses with modular arithmetic, for finding fractions in modular arithmetic, for solving that little like silly video game where we were moving a certain number of units in either direction. So an equation like this comes in handy a lot. It's called a linear Diophantine equation, which I probably butchered that second word just a tiny bit. So this type of equation appears in a lot of number theory situations, but we'll talk more in class about why this is useful. For now, we're just going to get these values. Okay, so let's do the same thing in this next example. So in this next example, we're trying to write 1 as a combination of 29x and 72y. Okay, and I want to use the extended Euclidean algorithm to do that. So what I did here, this is the extended Euclidean algorithm where I kind of work backwards as well. So in order to get started, we have to do the Euclidean algorithm. The 2 numbers we're working with here are 29 and 72. So I'm going to write 72 is 29 times something plus something. So ends up being 29 times 2 plus 14. Then 29 is 14 times something plus something. That's going to be times 2 plus 1. And then 14 is 1 times 14 plus 0. Okay, so the GCD of these two numbers is 1. Okay, so the extended Euclidean algorithm in the way that we're doing it here says forget that last line. In class, we're going to keep that line, so don't totally get rid of it. And now it says solve for the remainders in each of these equations. So in the top equation, I'm going to solve for the 14. So I'm going to get 14 is 72 minus 29 times 2. And then in the second equation, I'll solve for the 1. So 1 is 29 minus 14 times 2. Okay. And now we look at this and we say, what do we want to keep and what do we not want to keep? So we want a 29 in our final equation, but we want this piece to have a 72 and not a 14 or a 9. So what I'm going to do is I have this 14. The 14 appeared up here as a remainder. So I'm going to replace that 14 with this whole expression. Okay. So, okay. And I'm doing this in the equation where we have 1 is equal to something, since I wanted an equation at the end that was 1 was equal to something. So that's why I'm manipulating this equation. So I'm going to get 1 is equal to 29 minus this whole equation. So let's put that in parentheses. And then don't forget that that's all being multiplied by 9. Okay, now I've got to simplify this. So let's distribute the 9 to both of these pieces. So I'm going to have 1 is equal to 29 minus 72 times 9, because the 72 wasn't multiplied by anything first, so I can just say 72 times 9, plus, because the double negatives here, 29 times, I'm going to multiply the 2 and the 9 times each other, so times 18. Okay, and my last step is just to combine the like terms. So this term has a 29 and this term has a 29. So I have 129 and then 18 29s being added together. So that's going to give me 19 29s. So I'm going to have 29 times 19 minus 72 times 9. Okay. So this is exactly what we wanted. I don't really love the multiplication symbols in here, but we'll write them. So in this case, the x from up here, x would be 19, and then y would be negative 9, since I had written this as a plus in between these guys. Okay? So the extended Euclidean algorithm is always going to allow us to find integers x and y so that we can write the GCD of two numbers as a times x plus b times y, okay, where x and y are integers. So this is what the extended Euclidean algorithm allows us to do, is to write expressions like this. The previous two examples we did, the GCD was 1, so we were able to write 1 is equal to this combination of the numbers that we were working with. Okay, like I said, in class, we will learn an easier way to do the extended Euclidean algorithm, because notice in both of these cases, we had a Euclidean algorithm that only had like 2 real pieces to it. If we had tried to do the extended Euclidean algorithm on this very first example, we would have had to solve for all of the remainders and then do a lot of substitution, and it gets really messy to keep track of that. We'll do an example at the beginning of class like that, just to say like we don't want to do this, and then we'll learn kind of a nice tabular way of keeping track of everything. And then we'll also talk about like why we care about this, because this does seem a little weird and just kind of like mathematicians just doing some funny math.